Yo there, hey, welcome back. I know it's been a long time since I posted a video. Well, I would like to thank anyone who messaged me on Twitter or in Discord just asking me where am I, why you're not uploading any more videos. Well, I've been actually busy with finding an internship in, let's say, security research and stuff like that. So I wasn't that invested in YouTube, to be honest. Um, well, anyway, well, it seems out to be at the end that I was learning a lot of things, but if I'm not uploading videos in YouTube, then I'm actually learning something new. Anyway, so today's topic is going to be an interesting topic. I know a lot of you, especially CDF players, are interested in virtual machines and have tackled virtual machines in especially CDFs, and it's actually kind of not, let's say, not that beginner not that beginner challenge that you can try to solve while playing inside of the CDF. So today's topic is going to be virtual machines. I know the picture is silly, but I made some time just playing around with the pen and just trying to trying to draw this beautiful guy in here. Anyway, so virtual machine. So I'm going to be focusing on a specific type of virtual machine today. So I'm going to be focusing on the applications that uses the virtualization. So for example, a common example that we all know is actually the GVM. So GVM is a type of application level virtualization, which is quite interesting to be reverse engineering. Well, I'm not going to be reverse engineering the GVM. Obviously, we're going to be practicing that on a CrackMe, I suppose. Well, I'm going to be leaving the CrackMe binary in the description. Well, you can just check the description and you will find a binary. As always, you can just download it inside of your computer and play. But before that, as we usually do, we need to set up just some requirements so that we all have an idea on what virtual machine is. Since I have talked about the GVM, so the GVM is a type of application level virtualization. But the question is, what are the other types of virtualization? We can also have a pretty common example, which is the VMware, for example, Workstation 70 Player is a software that provides for you an access to other virtual machines, for example, which we call the full system virtualization, which actually emulates or mimic what the hardware is doing exactly on your operating system. So this is the example when we talk about full system virtualization. But when we talk about application level virtualization, such as the example that I'm talking about of the GVM, then we are actually talking about execution of some kind of programs inside of your operating system, but without a full virtualization. I'm not mimicking the hardware, which means I'm going to virtualize everything. So that means when we talk about virtual machine, we talk about virtualizing actually the CPU, the registers and the stack and the heap and stuff like that. So I'm not going to be virtualizing, for example, um, the network card or the audio card or stuff like that. I'm not going to be mimicking exactly what a computer is doing more than mimicking the hardcore component of what the computer is doing. So this is exactly what I'm going to be diving in today. So I have created this interesting graph for you so that you can understand. Well, we came back to the basics. We always came to the basics. So I'm pretty sure for some of you who have studied computer architecture know these three famously instructions, which are, well, I'm not going to be just calling them instructions, just we call them operations. So fetch, decode, and dispatcher, or execute, or whatever you can just call it. Anyway, so we usually see this pattern specifically about, or especially an application level virtualization. So when we talk about virtual machines, we usually see this pattern inside of the programs that were built specifically to run code. But before we dive into this architecture, I want to just give you the example of exactly what the virtual machine or what the type of virtual machines that we are going to be working on today is going to be doing exactly. So it actually take this box, so you can just call this a virtual machine. So it's going to be taking an input and it's going to be executing what the input is giving. For example, um, how do we explain this? So for example, the GVM is taking what the Java Virtual Machine compiler is giving. So the first thing to do is, for example, when we talk about Java, so you give Java code, so Java code, you give Java code, and then it gives you give that to the Java virtual, to the Java compiler, so Java C, and then it gives you a bytecode. So this bytecode is the interesting part that we need to be giving to the virtual machine, or to the Java virtual machine, that will be giving us or executing the Java code. So what the Java virtual machine was having is actually the bytecode, and it was actually executing what the bytecode is doing. Now the interesting point, if I want to reverse engineer the process back, I need to be able to the first thing to do, let's imagine that we don't know what the Java compiler is doing, and we don't know that Java code exists. And let's say that I'm in a customized world where everything is customized and I don't know any idea, or I don't have any idea about what the Java C is doing or the GVM is doing, and the only thing that I have is a binary that was generated using the GVM. Now the interesting point here is that I need to reverse back the GVM to understand exactly what was the bytecode that was executed, um, the bytecode that was executed, to be able to reverse back to the Java C and understand that there is something called Java code. This is just an example in a parallel world where we don't know exactly what Java is. Anyway, so I'm going so this is what exactly the GVM doing. So let's now talk in general. So a virtual machine in general is going to be taking some byte code. And I'm always talking about application level virtualization, where we want to virtualize an application. So the bytecode is actually going to be containing the program that will be executed. And what the virtual machine is doing, it's going to be interpreting that bytecode, dissected, let's say disassemble that bytecode and then make sense of it and then execute what the bytecode is supposed to be executing. So this is what the bytecode is doing. So if we go back to the process now, or to the architecture that the virtual machine is going to be built upon. So this is just a general representation. It doesn't mean that each virtual machine should stick to this order, but this is more like a general template where when we talk about virtual machines. Anyway, so we have the pre-initialization, and we have the init, which is the initialization, and we have the fetch decode dispatcher and few handlers, and then we have the virtual machine exit, and we have then the next. So the next is going to be pointing back to the initialization, and that will be fetching the next opcode. Now the thing is, there is some kind of keywords that we will be using a lot, and the main thing that is going to be happening, or the main questions that we need to ask is what the fetch is going to be fetching exactly, and what am I going to be decoding, and what am I going to be dispatching. Well, the thing is that since the virtual machine is taking a bytecode, well, we need to be working exactly on the bytecode. So the bytecode could be something like this, for example. So it could be, for example, 6e, 2f, 3, 1, etc. So this is what a bytecode is. It's more like any kind of program or any kind of thing that we have so in the videos that I have created. So the thing is that now, since we have the bytecode, how can we make sense of this bytecode? So since the CE and the 2F and the 3.1 and etc. is going to be giving something, we need to make sense of that. So this is actually called an opcode. So any kind of opcode, so we can just always go back to the root. For example, when we talk about, for example, um, Intel 86, for example, when we say move EIX 0x1, we all know that this is going to be translated to a machine code, a machine code instruction, which for example could be pointing to, just an example, could be pointing to 2 3 1 1 1, for example, and 3 2, and then 0 1. So 0 1 is the parameter, for example. 3 2 could be pointing to the EIX, and 3 2 11 could be pointing to the move. Now the thing that now the thing that we that we have now, the 2311 pointing to the move. That means that we are trying to decode these instructions just by using our eyes. But the thing is that when we want to say to the computer, hey, I want to be decoding this 2311, then we should try to make sense to the virtual machine itself. So this is exactly what was happening. Just so by assuming that we know this, by giving this bytecode, we can make sense and just disassemble this bytecode just to let it go back to assembly, for example. Anyway, so in this case, I'm not going to be dealing with the Intel 86 or 64. I'm going to be assuming that the programmer who created the virtual machine is creating a custom virtual machine, which means that the virtual machine is custom, which means that the bytecode is customized and the opcodes are customized, and there might be also sub opcode. So this is a sub, so for example, this is an opcode, and the next opcode to the next opcode to this opcode is called a sub opcode. So so this is just some syntax that we will be using a lot when we try to deal with stuff like this. Anyway, so now when we go back to the architecture that we are trying to analyze, so the fetch um, is going to be completely just preparing what the virtual machine is going to be executing, loading all the details of the instruction, analyzing what the instruction is going to be doing, and just forwarding the result to the decoder that will be decoding the instruction, and then trying to decrypt any kind of, let's say, instruction. Well, the thing that I'm talking about is, in some cases, guys, when you try to just reverse engineer a virtual machine, and we will try to do that on a practical view, you will see that sometimes the instruction is encrypted, and when the decoder is going to be executing some kind of instruction, it needs to be decoding that instruction, which means it needs to be decrypting sometimes the instruction. It's not always, but sometimes the instruction is encrypted, sometimes it's not. So you have to find a way or figure out a way on how to do that. So by practice, the more you reverse engineer virtual machines, the more you understand this behavior more, or the more you see this pattern that I'm showing right now to you. Anyway, so the dispatcher is going finally to forward to the right handler that should be handling the instruction. So for example, if I pass down 6E, so the dispatcher is going to be passing the execution flow to the handler that handles this opcode, which is 6E. And then after that is going to be pointing to the next opcode that will be executed and doing the same pipeline. And then there is this special handler, which is the virtual machine exit, that will be exiting what the virtual machine is doing. I suppose this is enough for an introduction, and now we should be able to start doing some virtual machine practice, I suppose. So the challenge that we will be practicing on today is called Kata VML1. It's actually a virtual machine crack me. So I will be leaving the binary in the description so that you can download it and play around it as much as you want. But we go with always with the same flow of the instructions that we have, or the stuff that we have learned in the past videos. So we start by running file on the Kata virtual machine. We see that it's a 64-bit binary that is a little Indian and dynamically linked. So all the binaries are all the libraries, I'm sorry, all the libraries are going to be used by my computer, so the interpreter path and stuff like that. So if you try to run the binary, you see that it's asking for some kind of input. I'm going to be giving it some kind of input, so A, B, C, D, E, F. So it's invalid, try harder. Okay, so this is basically a basic crack me that we always see in CDFs or in real life or whatever. So if I try to run strings to this SCADA virtual machine, v1, so what do we have now? The thing that we should be able to spot is that we have two kind of messages, which is correct or try harder. Now the thing is that there is no much data to be looking at when we run strings, so the best way now to start tackling this is by dropping it in IDA. So we need to drop this in IDA. So I'm going to be opening this in IDA. So we just drop it in IDA. I'm going to be using all the default settings in IDA. I'm not going to be changing anything. So it's going to be analyzing what this binary is going to be having. So as you can see, IDA just drop us exactly to where the main is. Okay, so what do we have? So we also, do we have anything special in here? Nope, we don't have anything special. So we jump back to the main. So this is what the main function is doing. A pretty standard allocation of variables which we know, which is the allocation of the stack frame of the main. And then he's calling some kind of interesting function called sab12d0. Then he's testing if the AL is 0, then he's going to be printing correct. Otherwise, if it's not 0, then he's going to be taking us to this flow, which is invalid harder. So without any kind of hesitation, we try to see what this sub is doing. Now this is what the virtual machine flow looks like. I know for some of you, someone might fear just looking at this graph flow and saying, oh my god, what does this virtual machine is doing exactly? Do I have to read all of that? Well, actually, how much time does it take me to reverse engineer this virtual? I think it's around 6 days, 5 days. Well, the things that around the second day, I have already just reversed engineered the 70%, 18% of the virtual machine, and the harder parts were actually those 4 blocks. Anyway, I'm not going to be just skipping the challenge for you. We're going to be doing it from scratch. Anyway, so we go and check the data that is going to be allocated on the stack. So we are now inside of the, let's call it the virtual machine core. So this is the virtual machine core, or let's say the virtual machine itself. Anyway, so it's going to be pushing the 3 registers, saving them on the stack, and then it's going to be allocating some interesting amount of bytes in the stack. So variable 100, 1018, 2018, and 3018, and then allocating more bytes to the stack. So the more you subtract from the RSP, you are actually allocating data on the stack, and we already understand that along this series of the reverse engineering we've been trying to build knowledge together. So I suppose now I don't have to explain a lot about those little fundamentals that we have talked about. Anyway, so we know we also, so after allocating some data on the stack, now he is moving 3b1a, so 0x3b1a to the edx, and then he's loading the effective address of this um, of this offset, which is 3008. So he's basically loading this address to the RSI and then XORing the R12 with the R12, which gives us actually 0. So he is zeroing the R12D. What else do we have? So he's moving to the RAX, this FS word, well, keyword, well, quad word 28, which is actually so it's actually a pretty known segment, or a pretty known segment in the binary, which is actually resolving around the stack canary. So I'm going to be just calling this the stack canary. So this is the just to mitigate the buffer overflow attacks. So yes, so he's going to be moving that inside of the REX, and then he's moving that to this offset. So the stack canary should be at the end of the stack. So yes, so if you look at the layout of the stack, we have this variable, 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 and the stack canary. So if you try to change any, so for example, if I try to find a way, or if I find a vulnerability that is in here and try to get to the stack return address, actually, if I want to return to any kind of place, I'm not going to be doing that unless I figure out a way on how to find the value of the stack canary. Anyway, it's not going to be a buffer overflow video, so we keep focusing on what we have in our hands. So we're XORing EIX with EIX, which again just resolves on saying EIX equals to 0. Yeah. So, and then we have the destination. We are moving the effective address of the destination. So we are moving this address actually. So when we say RSP 3B78H and the destination, so it's this one. So when we do this with this, we are actually just talking about the top of the stack, because RSP RSP is basically pointing to the top of the stack, and plus 3B78 is actually the top of the stack. So that means that this is the top of the stack, and when we do plus destination, we are just getting below the top of the stack. So we are just trying to downgrade the RSP down. Anyway, so this is actually the address of the destination and the stack. We are loading that effective address inside of the RCX, and then we are moving with the what's inside of the RSP, which is the top of the stack, to the RBX, and then we are moving the RCX to the RDI. So, and then we calling memory copy. So memory copy takes three arguments: the source, the destination, and the end. And is how much data are we going to be copying from the source to the destination. Now the thing is that the source is this place, which means that he's going to be copying those bytes to this destination. Now I'm not going to be giving too much attention to the destination more than the source. So the thing is that since we are dealing with a virtual machine, as we have said, then we should be just understanding that this place is actually the place where the virtual machine code is residing. So that means this is the bytecode that is going to be executing by the virtual machine. So as we can see, we are actually seeing a pattern that I have talked about. So this is F6, CE, 49, D3. This is more resembling like something we know as bytecode. So he's actually copying the bytecode of the virtual machine to this destination that he will be next executing. Okay, so this is for now a good, interesting introduction, or a good interesting entry point that we can start with. So since we know now that we have the bytecode that will be copied to this destination, then we should track down where this code is going to be executed exactly. So okay, let's proceed along the program just to see more what is going to be happening. So next instruction is going to be packed XOR. So packed XOR is going to be executing an XOR operation on a 128 bits register. So XMM 0 to XMM 7. It's not more like of the general purpose registers that you know in Intel. So basically the XMM is a 128-bit register, and it's used actually for multimedia and images and graphic stuff. So it's basically used for a, let's say, more intensive data consumption. So for example, when you have a value that is big enough, then you are going to be using XMM0 maybe. Anyway, so that's back to XOR. So he's going to be XORing the XMM with itself, which resides to the conclusion that is this XMM is going to be having a 0. Anyway, so then he's going to be moving what's in the XMM to this variable. So I'm going to be calling those two variables register 1 and register 2. And I'm going to be explaining exactly why I'm going to be calling them like that. So register 2 and register 1, and I'm going to be lately explaining exactly why did I call them like that. Okay. Okay, so um, what do we have? So since we know that this is going to be moved to register 1, and then he's moving what's in the REX. So memory, by the way, memory copy is going to be um, returning the result to the REX, and we already know that any kind of function is going to actually be returning the result to with the REX. So the REX is supposed to be pointing to the new chunk of data that is pointed to by the destination, which is the virtual machine code. So he's moving that to the RDX, and then he is going to be moving what's in the XMM again to the register 2. Okay, now until this point, if we go back, for example, to this one, we see this pattern. As you can see, a lot of errors are actually just going back to this block. Well, this block resides exactly to the one that I have talked about, which is this one. So it's more like the initialize one, where we want to be starting to see the pattern that I have talked about. So so it's pretty common pattern, as you can see. So with those, all those blocks are always residing to executing something and then going back to this block. Anyway, now the thing that I can proceed by doing that statically again and keep on going by doing this, by doing that statically, just trying to reverse the code statically, just as we tried to do it right now. But the thing is, it's going to be a lot harder to do that, and I want to be more accurate about what I'm going to be saying or what I'm going to be reverse engineering. And by accuracy, I mean I want to know the value of the register. So I'm going to be using a debugger. So it's time to debug that. So if I want to debug, so I need to be going inside of um, we go back a little, so we go back more a little, so I'm going to be opening up program files, IDA debugger. So we need to go to debug server. So now we have all the debug servers, so I'm going to be running the Linux server, so it's running. We go back a little, and I'm going to be actually also just setting a breakpoint in this one. So to set a breakpoint in IDA, you just press F2, and then you run the debugger. So we give it um, local host, and yes, it's starting, I suppose. So okay, use found. Okay, so we hit the breakpoint. So those are the registers. So I'm going to be just taking just a second. Well, I'm not going to be using the local types. So I want those ones to be like in here. Yeah, I want to see all the registers exactly. Yeah. Anyway, so the thing now, since we know what the RDX is having, so we see that the RDX should be pointing to the destination that we have talked about, which is, as you can see, is pointing to the virtual machine code that we see. If you go back to the RDX, what is the RDX? RDX is also pointing to the virtual machine code that the virtual machine is going to be executing, which is 6F, CE, etc. So now, okay, so since we saw that, so Now he's going to be loading actually the effective address pointed to by this one, so that means that he is going to be moving the RDX plus 1 to the REX, which is actually, if we now try to press F7, well, F7 is going to be stepping back. Well, the thing is that there is an exception handling. So that means that the programmer is actually, so this is an alarm actually. So this alarm is just saying to the program, after an amount of seconds or minutes, you need to be stopping the, let's say, the execution of the program or whatever. So but somehow we have just passed that, so we don't have any kind of problem. We can just keep on debugging without any kind of issue. Anyway, so now if you go back to the REX, we see that the REX now is pointing to the next byte aside from the first one. So the RDX is pointing to the 6F or the F6, and the REX is pointing to the CE, and now he is moving that value to this variable. Now the thing is, now this is a pattern that we also see a lot on real programs, and this pattern is actually the there is some kind of special register that we see a lot, which is the instruction pointer. Now the instruction pointer is actually this one, and I'm going to be calling it just virtual machine instruction pointer because it's actually saving the next instruction that will be executed. And by doing that, we just see this pattern. So he's moving the next instruction to the REX and then loading the effective, well, he's loading that instruction to this virtual machine instruction pointer. So this virtual machine, besides from just assuming me that this is register 1 and register 2, and I'm going to be explaining why these two values are actually registers, there is also the virtual machine instruction pointer. So we're seeing some kind of way of emulating what a computer is doing just in this little virtual machine that we are trying to dissect together. So um, now the next instruction that will be executed is that now we see that he is going to be accessing what the RDX is pointing to, and he's moving that value to the EIX, which means that EIX now should be having um, F6. And now if I press F7, we see that now the REX is having F6, which is the instruction that will be executed, or the opcode that will be executed, for a better understanding of what this F6 is doing. So he's going to be comparing the AL, which is the lower part of the REX, to 0x AA. So okay, so he's going to be comparing that value with AA, and if it is 0, which means that it is equal to 0x AA, he's going to be executing this workflow. Otherwise, he is going to be executing this workflow, which will be jumping. So he's going to be doing some checks. So what if we try, for example, to see exactly what this instruction is going to be having, what this opcode is going to be doing exactly. So I'm going to be trying to jump to the handlers of the 0x F6. So it's not 0, so he's going to be jumping in here. So it's not above, so well, it's actually above. So if it is above, then uh, um, he's going to be jumping to this location. So okay, since it's above 0xAA, so if we compare it to the 0D5, it's actually not 0x d5. So if it is below or equal, and yes, it's not actually below or equal, it's still above, we're going to be comparing to 0x ef. So if it's not, well, it's actually not, we're going to be now going to the 0x f6, which is now actually the handler of this one. So if you press, now it's not, well, it's actually equals to f6, and now this is the code that will be executed when we send the opcode f6. So it's going to be now fetching the next instruction, which is 49. So as we can see, if we go back to the RDX, so the RDX is having f6 and having CE and having 49. So now again, the virtual machine instruction pointer is just trying to save the next of the next instruction, which is, as you can see, 49. And then he's actually now, instead of loading the opcode itself, he is now loading the sub opcode just after what the RDX, um, just after the F6, yes, which is CE. Now just I'm going to be skipping, so yes, so this is the instruction. So this the EIX supposed to be having now CE. So yeah, it's having CE, and now he's actually moving that sub opcode inside of the ECX, and then he's ending it with 3, and based on the result, he's going to be doing something. Now, what does this behavior is exactly? And what is this pattern? Well, if you go back a little, so just imagine this as this one. So this is CE. When we ended with 3, so this is written on 4 bytes. So on 4 bits, I'm sorry. So the E is the same. So what is the E exactly? So the E is supposed to be so A is 10, B is 11, C is 12, and D is 13, and E is 14. So E is 14, so it's 1 1 1 and 0, and C is 12, so it is 8 with 3. So 8 9 10. Nope, it's not 3. Okay, I'm not going to be using a lot of my ad. I'm going to be just directly bin of C. Okay, bin of C. Uh, direct C. Yeah. So it's 110. Anyway, uh, okay, just a second. Can I refresh that? Yeah, 110. Yeah. Anyway, so he's going to be ending this value with a 3, which is this is the 3. So 0 0 0 0 0. So he's actually trying to get those two values. So we have 3. How many keys do we have now? Now this is the interesting question. Now this is the interesting question. How many keys do we have? So when we take, for example, when we take this value and CE and we end it with, so 0x, and we end it with 3, how many values how many result can we have? Well, when we end something with a 3, we can have E0 0, which means they are completely different. We can have E0 1, which means they have one bit that matches. We have 1 0 and we have 1 1, which means that the both bits of both the lower bits are matching. So we have 4 cases. So this is what should be happening in here also. So he's going to be checking the 4 cases. So this is the thing. He's going to be giving the opcode, which is F6. He's going to be giving the sub opcode, which is in this case CE, and based on the opcode he's going to be executing some workflow. So when we change the sub opcode, um, the complete instruction can be changed, which means that to change, for example, the behavior of some kind of opcode, it's basically change it based on the sub opcode. I don't know if you understand that or not, but let's take a look at what is going to be happening. So it's not equal, since the ECX in this case it's going to be 2, so it's not a 2. So basically he's checking. If we end the ECX with 3, it is going to be giving giving a 2, which is not a 3, which means they are not equal. So if we compare now the lower part of the ECX, which is CL with 2, it's going to be giving us a 2. So now we execute the block. So he's moving what's in the ECX, which is what's in the RDX plus 2, which is that 49, into the ECX. So this is, well, he's actually moving not the 49, because he's not specifying byte PDR or word PDR or double word PDR. He's automatically getting as much bytes as we can to fit into this ECX, and we know ECX is 32-bit register. So he's going to be passing down or moving down 4 bytes of data inside of the ECX, which we can see 49 3D AC E7, which is in the little Indian. If we go back a little, so he's actually taking those 4 bytes, as you can see. So F6 is the opcode, CE is the sub opcode, and 49D3 AC E7 is actually the value that will be passed to this opcode. So it's more like a parameter. So and then we see 0xAA, and you can now imagine that this 0xAA should be actually the next opcode that will be executed. So anyway, now if you go back now and we see, so he moves, he shifted left, he shifted to the right, I'm sorry, the AL, which means the sub opcode that we have, and then he is adding to the RDX6, which means that he's actually just F6 CE 49 D3 AC E7, which is actually 6 bytes of data. So he's actually trying to move the EDX that is actually pointing to the virtual machine code to the next instruction. So that means that the instruction size is 6 bytes. So we step one more, and we see that the EIX is now ended with a 3, which means now we see 0, 0, which means that now he is going to be moving the value that we have loaded from the virtual machine code bytes into this location inside of the memory. Now RSP plus this one is the top of the stack, plus register 1 plus ARIX by 4 is actually now an interesting way of accessing memory. Now the thing is, now we see that the EIX is ended with a 3, guys, and using the same methodology that we have used when we tried to dissect the way that the sub opcode was loaded, how many values can be generated using this instruction? When we end something with a 3, we either have a 0, we either have a 1, we either have a 2, or we either have a 3. So we have 4 cases. So in this case, it is going to be the same. And the thing is that since REX could be taking either 0 or 1 or 2 or 3, so that means that we have 4 values to be trying. So this is why he is actually multiplying it by 4 and adding the register 1. And now the thing that is now accessible and really interesting is that by seeing this pattern, I have came to the conclusion that register 1 is actually having 4 bytes of, or 4 values that should be accessed. So this is E4 bytes, and this is E4 bytes, and this is E4 bytes, and this is E4 bytes. And the way we access those 4 bytes, so this is the register 1. So, and the way we access those four values is actually by trying to change the REX that was already generated using the sub opcode itself. If we go back a little, so we are actually getting the sub opcode, shifting it to the right by 4 bits, and then ending it with a 3. Just by doing that, we are actually generating something called the index that we want to access exactly. So in the register 1, we have 4 ways of access. We have 4 actually 4 places or 4 cases, or I don't know what you can call them, and each one is going to be having 4 bytes of data. Yes. Anyway, anyway, so yes, so after doing that, he's moving that. So he's moving the result loaded inside of this register pointed to by REX, and then he's going to be going back to the handler. Now, I can keep it. We will actually keep on doing that. But the thing is that it's time, guys. Now, since we know what the virtual machine is going to be doing, it is time to mimic what the virtual machine is doing and write a disassembler. So it's time now to write a disassembler, and by writing a disassembler, I mean we should be trying to um, write a disassembler for the virtual machine, and by that I mean we should mimic what the virtual machine is doing, but in our own way. I'm not going to be using always what uh, what the debugger is going to be giving me, more than just trying to do it independently of the code itself. So if you go back, I want to be writing a disassembler for this one. So disassembler dot python. So yeah, we're going to be just applying the same methodology that we have already done with the other challenges. So what is the best way to approach this, guys? How can we start writing to the disassembler? So the first thing that we already can think about is we should be isolating the virtual machine code out of this binary. So we should extract the virtual machine code. So how can we extract the virtual machine code? There are two ways. We can either copy all that range of bytes, or all those bytes just manually from IDA, or just use the IDA API. Since we can use that, I can just directly, for example, just import I'm going to be importing ADA API. So this API is actually can let us interact with IDA. I'm going to be just calling I'm going to be opening up a file. So open a file, just call it virtual machine code .txt, for example, and I'm going to be opening it, for example, in write mode. um, what else can we do? So I'm going to be just trying to get the address of this, the first byte, which is this one. uh, yeah, and what am I going to be doing exactly? So I'm going to be going in the range for I in the come on, in the range of what exactly? So if we go back a little, so we know that the size of the code is going to be 3b1a. Yeah, so it's going to be 3b1a. So virtual machine code dot write. So I'm going to be writing something to the file. Well, I'm going to be writing the hex of the IDA API dot read, or let's just get byte located at the address plus I. Well, the thing is, you want to be also getting rid of the 0x. And yes, so by doing that, if we try to run that inside of IDA, so we go to file, script file, and run this assembler. So it should be working, I suppose. Yes, it's working, and we have extracted all the data from IDA. If you go back to the end, we have 4AFA. If we should be trying to check that out, well, we should be checking the first byte. The first byte is F6CE493. Well, it is right. We should be checking the end just to see that we have extracted all of it. So I want to print the address plus this one, and I want to just print it in hex too. Yeah, should be going back to IDA, disassembler, and yes, so this is the address. We take it, we press G to be jumping to address, and it's actually 0xa. Okay, so if we go back a little, so the virtual machine, okay, so there's a problem when I have tried, so it's actually not overriding the first one. Why is the code now bigger? Some kind of weird thing. Anyway, 0 for D5. So we have D9, D9, 0 for. Well, this is actually 0, 0, not 0, 4. Well, this is 0, 0, and this is 0, 4. Anyway, what else do we have? You need to be checking the 8. 2D 8 E7. I want to be z-filling that maybe. Can we z-fill that? Anyway, it doesn't matter pretty much a lot about. What does it matter? Hmm. Hmm. I don't know. What is the best way to do this? Can we z-fill them or not? Well, I'm going to be assuming that we don't have to do that. Well, just let me do this one more time. Okay, one more time. I think everything should be okay. I'm just going to be now emitting, just commenting that those files, just using now. Going to be just trying to just add the shebang, which Python 3, so it's located in this one. Okay, so I'm going to be using file open. I want to open virtual machine code.txt on read mode. Okay, disassembly. So I'm going to be also creating a file, guys, for the disassembly that we will be generating. So virtual machine, so disassembly.txt. Uh, yes, and the content I want to read them. Read the content of the file. And the virtual machine code is supposed, I'm going to be converting it from hex, since it's in hex, the content, so it's bytes. I want also to print the size, just to check that we have dumped all of the bytes that we need to be dumping. So what is the length of the virtual machine code? I need to be knowing that. Yeah, so okay, so I want to be writing that in hex. Uh, so it's 0x318d. And how much data do we have? So 3 um 18d. Okay, so it's actually not taking the case of the zeros and the z-fill and all of that. How do we know this? 3x maybe. Okay. So we should be adding so the z-fill, so we didn't z-fill them together because z-fill. So I want to be adding so 2 bytes to each one of them. So I'm going to be converting them to hex, and then if there is any kind of byte that is not in there, so the z-fill is going to be filling the rest of the bytes. So anyway, I'm going to be discounting those. Okay. Script file, disassembler. So try it again. This file is not written. Okay, if we go back a little, so we have 0, 0. So suppose the z filling has worked. We can check that, so we can just now comment what the IDA API is going to be doing. Just commenting back those things. What is the length now? Now the length is supposed, okay, now it's right. So 3b1a, which is the length that we need to be having. So we have successfully just retrieved all the virtual machine code out of the file. Now we can, for example, now try to iterate through it. So while the I is inferior to the length of the virtual machine code, or to just directly, well, we can just use directly the virtual machine code. Yes, the virtual machine code. Okay, so we can just directly be using that one. So if the I is inferior to the length of the virtual machine code, I wanted to just get the opcode. So the opcode is supposed to be what? It's supposed to be the virtual machine code at the position I. So this is what the opcode is, and the sub opcode or the sub op is supposed to be the virtual machine code and the instruction I plus 1. So if the virtual machine code is, now we go back to IDA. So if the virtual machine code is 0xf6, okay, I suppose we are, am I in the right path? So it's not above, so it's not 1, it's below or equal, it's not Z, yes, it's this one. Okay, oh nope, it's this one. Okay, so if the virtual machine code of I is equal to 0xf6, so if it is f6, then what should we do? So the first thing that I want to be printing is to print the hex of the sub opcode, just to check that we are on the right path. And I want also to be, how much data are we going to be jumping? Well, anyway, I'm not going to be checking that right now. Well, we have to increment the I, so I equals to I plus 1, just to make sure that we didn't get, or that we don't hope or get into the infinite loop. Okay, so for now I think this is okay. So I want to be printing the sub opcode, and yes, so this is what I want to be printing. So if you try to run that, so index out of range. So what if we try to get this one like that? Now we don't get index out of range, we are cool. Okay, we don't have any problem now. Okay, so how do we know that this thing is now working or not? Okay, so I want to be now mimicking exactly what this opcode is doing. So we have the register as we have talked about. So register is going to be having 4 values. So 1, 2, and 3, and 4. Okay, so this is now going to be pointing to the virtual machine. So the virtual machine instruction pointer is going to be having RDX plus 2, which is actually I plus 2. So the RDX in this case is going to be I in the Python code that I'm trying to write. So this is what the RDX is going to be having. So the virtual machine instruction pointer is going to be I plus 2. And now I'm going to be moving RDX plus 1 to the AIX, so which means that I'm going to be accessing that one, which we already did by just doing the sub opcode. So the AIX is equals to the sub opcode, which is pretty like quick way to do this. And the ECX now is supposed to be equal to the AIX and 3, so its AIX ended with a 3. Now we came to the cases where we have to branch. So if the ECX is equal to if we end the ECX and 3, and if it is equal to 0, so if ECX is equal to 0, you're going to be something else if ECX is equal to 2, which is in this case comparing with the 2. So if it's not, so he's going to be exiting. So this is the exit, by the way. We can just give colors if we want. So this is the exit. I'm going to be coloring it with this one. And if we go back a little, so I'm going to be doing also some other interesting coloring just to color the handlers too. There's going to be this. So when we look at this graph like that, we see that we have colors which make sense to the special blocks that we know. So anyway, so we go back a little. So yes, so it's equal to this one. Nope. So it's equal to this one. So if the ECX now is equal to 2, what is going to be executed? Yes, okay. So it's going to be, so if it is a 2, it's going to be shifting right the EIX as we can see. So the AX. So by the way, when we say AL, so AL is the lower part. So I'm going to be using AIX as a way of just defining the AL, defining the REX, defining everything. So when we talk about any when we use the accumulator register with anything, I'm going to be using EIX. Anyway, so shifting right the EIX with 4, so EIX shifted with 4. RDX is added 6, so we add 6, which is the length of the instruction itself. Um, so I'm going to just print anything in here just to get rid of that error. Okay, EIX now is ended with a 3, so I'm just going to be adding it directly in here. So it's ended with E3. So he's ending it with a 3. And then he is actually moving what's in the register 1, what's in the ECX actually. I forget the ECX. Wait a second. We forget the ECX. Okay, so before that, the ECX is supposed to be having loading 4 bytes of data starting from this one. So we can just directly, so um, int from bytes. So I want to virtual machine code starting from the position 2. Starting from which position? It's actually I plus 2. Yeah, I plus 2 to the 6. To the I plus 6, yeah. Like that. And the byte order is should be in this case little Indian, I suppose. Yeah, it's little. Yeah. Um. Anyway, so if you try to use this one, so if the I is pointing to the opcode itself and the plus 1 is pointing to the sub opcode, then the I plus 2 is supposed to be pointing to the values that we should be fetching from the memory, and I plus 6 is supposed to be the ending, which is so 6 minus 2 is 4, so those are 4 bytes. So if you subtract I plus 6 minus I plus 2, the I gets eliminated and it gives us a 4, so that should be okay. Okay, so this value is supposed, so register exactly pointed to by EIX. As you can see, the index is generated using the EIX is supposed to be ECX now. So now what I'm going to be writing inside of the virtual machine disassembler that we have opened. I'm going to be just writing into the disassembler virtual machine dot write. I'm going to write move into the register pointed to by EIX, the value pointed to by ECX, and getting back to the line. Yes. So this is what the ECX, so this is what this case is going to be doing, and so this is the disassembly of it. Um, what else do we have? So basically, what else can we do also? Okay, so we can now check the other case since this is going to be taking us to this one. So we can go back and check the other case in case it is equal to 0. So if it is equal to 0, then he's going to be moving what's in the AIX into the ECX. So ECX is equals to AIX. And he's going to be shifting that with 4. Shifting the X. I suppose he's going to be ending. So he's ending those two. So I'm going to be directly. So he's trying to access now some kind of indices or indexes or whatever. So the index is going to be also in the ECX. So he's moving now to the right AL with 4. We did it. He's adding 5. So the instruction length is going to be 5 in this case. Okay, and then he's moving, shifting right ECX, so ECX shifted with 6 this time instead of 4. and I suppose it should be ended with a 3, as we can see in here. And then he's accessing now to, and as you can see now, he's moving one register, one value inside of a register into another register. So this is like more like swapping registers together, or just moving values from registers. So he's moving the value that is in the RCX, or the register 1 pointed to by RCX, to the ECX. So if you can just do it like that, so ECX is going to be register pointed to by ECX, and a register pointed to by EIX is equal to ECX, which is this one. So what's actually been happening if we write in the disassembly of the virtual machine is that he's going to be he's moving what's in the register EIX inside of the ECX, which is this value right here. And then we should be going back to the line. And if we go back, so we have successfully just finished the first sub opcode. So this is what the first disassembly of this sub opcode should be doing. So else, you should be just adding I equals to I plus 1. Okay, otherwise he's going to be continuing. If this happened, and I want to also check the next instruction that will be executed. So next is going to be next. Well, it's not next. Well, it's actually virtual machine code pointed to by I, and I want to hexify the value. Yes. Yes. Anyway, now since we have that, so we can try to run that. So I want to break just to check the first instruction. So he's going to be moving this sub opcode and then moving that one, and exactly doing what I want him to do. If you go and open up now the virtual machine, so we see that moving register 0, he's moving that value, which we already see. If you go back a little, so we go back a little just in here. So this is the one, so it's not equal to 0, it's not a 2, so it's this case. So if you go back a little in here, we see that if we just put a breakpoint in there and just rerun the program again, so I'm going to be stopping, running again. Okay, so so we hit the second breakpoint and we press F7. So we see that the ECX is having this value, which is E7 ACD 349, which is the same as this one. Now, good job. We did a pretty good job there. So now we can just get rid of the breakpoint. Disassemble again. Disassemble again. And we see all the values loaded, as you can see. So we see a lot of values inside it. So there is a lot of moves that was actually happening inside of this binary. Yes. Anyway, so this is what was happening. So this is really interesting, I think. Now we should be able to do the same pattern with the other opcodes too. So now what I'm going to be doing is that first thing I need to get rid of this breakpoint. So by pressing F2 we just cancel that breakpoint, and now we can just go back to the pressing F9 will get us to the next breakpoint that is already in there. So well, we have this all around. Okay, so we are back in here. So the next breakpoint I want it to be always in that compare, just to see the opcode that will be executed. We can get rid of this breakpoint too. Anyway, so F7, F7, F7. We are now executing 0xAA. Okay, so if we check this flow, the flow of this opcode, press F7. So it's going to be taking us exactly to this one. So we need to go back in here. So continue. Oh, we don't need this one anymore, and we don't need this one anymore. So okay. So else if the virtual machine code of I is equal to 0xAA, what do we do? We do the same thing. We take the virtual machine instruction pointer should be pointing to the I plus 2, which is these two instructions, and we load the sub opcode, and then we do so EIX equals to sub opcode, and ECX equals to the EIX and 3, and based on the ECX we do some kind of pattern. So if it is equal to 0, as always, print something, and then else if ECX is equal to 2. Okay, we will see if there is any kind of 2. So if it is equal to 0, then you go in here. So if it's not, we will see what's going to be happening. Pressing F7, so F7, 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 F7. So it's at 2. So if there is any, if the ECX is equal to 2, what is going to be happening? Let's see what the flow of the program, where it will be getting as exactly. So F7, so it's going to be shifting left the EIX. Okay. So EIX equals to the EIX shifted with 4, I suppose, to the right. Yes, and I suppose since we are shifting to the right, as we can see, the pattern is repeating itself. So he's supposed to be ending it with a 3 just to get the index of the case of the register that we should be accessing exactly from those 4 bytes. So we go back a little. So EIX equals to EIX shifted with a 4 and a 3. And then we are adding 8 to it. So adding an 8 would always get us this one. So ending it with a 3. So adding to the RDX 8, we did it. So ending, we did it. So register is moved into the ECX. So ECX. ECX is equal to register of EIX, I suppose, since this is an REX, and as I have explained, I'm going to be just dealing with them as the same register, which is EIX. And then he's going to be subtracting from the RDX minus 6. So how can I fetch this value? Now this is the question. Now we are going to be fetching from the RDX minus 6. Okay, so we need to be stepping a little. Okay, so we're stepping back a little. Okay, so how do we know this? So we have RDX, so we have to mimic that one too. Okay, so we have registered that one. So we need to subtract. So ECX equals to ECX minus hex of the value that is pointed to by okay, that is pointed to by what? That is pointed to by ECX equals to ECX minus what? So we need to be getting those values from the RDX minus 6 from the code. So from bytes, yes, okay. So from bytes, so what do we have? So I'm going to be taking them from the virtual machine code, pointed to from minus 6 to minus I minus 2. Well, if we do I, well, this is the one that we are getting. So I minus 2 minus I minus 6 gives us 4 bytes. So this is okay. So we do the byte order. So it is going to be in the little endian, obviously. So this is the subtraction. So I need to disassemble that. So I need to note that. So right, um, sub from what exactly? So we're subbing from register in the EIX, the hex value that is actually pointed to by this instruction, I suppose. Yes. What is next? So we need to be loading that one inside of the register pointed to by EX. So register EX equals to ECX, and we need to add one to the disassembly too. So we are moving what's in the register EIX to the hex of um, hex of the ECX. Yes. And we shouldn't be forgetting also to add, to go back to the line. Yes. And now should be okay. Now everything should be okay. So what else do we have? Nope. Okay, everything is cool. So else I should be equals to I plus 1. And we continue. Okay. So what is the problem in here? So the key is 0. Okay, we didn't handle that. So suppose that should be going back to the little. So we go back a little. So it's not a 2. So if it is the other case, which is now equal to 0. So if it is equal to 0, then we have the first thing to do is to load what's in the EIX inside of the ECX, and then do shift right by 6 to the EIX. So EIX is shifted. Um, AIX is shifted to the right with 6, and it should be ended with a 3, I suppose. Okay, I suppose it should be ended with a 3. What is the AL? So yeah, it's ended with a 3. And same goes for the ECX. So ECX is ECX shifted with 4 and ended with a 3 to create the new indis. And then I is equals to I plus how much this time. So the instruction size is 6 this time. So it is 6. So now we have finished all those instructions. Now it comes to doing some instructions. So we're getting ECI into the game. So ECI is equals to the register pointed to by what? So by RCX. So it's ECX, and then that value is going to be subtracted. So ECI is equals to ECI minus the value that is pointed to by EIX. So register EIX, and then the ECI is moved to the register by RCX. So register of EIX equals to ECI. Okay, so we need to disassemble those 3 instructions. So disassemble dot virtual machine dot write. So I'm going to be subbing what's in the register pointed to by ECX, the value that is in the register of, well, it's always in hex. Well, the value that is pointed to by EIX or ECX. Yes, it's EIX. And then I'm going to be disassembling virtual machine dot write. Move what's in the register EIX, the value that is pointed to in the ECI. It's in the ECI, right? That's hex ECI. And we don't forget to go back to the line. So I suppose now everything is okay. Uh, suppose now everything is okay. Do we have any kind of problem? Nope. We have successfully, I think, reverse engineered this opcode too. So this is what this opcode is going to be doing. Now if we try to run the disassembler again, so okay. Now if we try to just get that back here, run again. Okay, so we have E7 and he's subtracting register 0, um, AC D3 49, so he's moving those two registers. Wait a second, like if I go a little, so the value that was loaded inside of the ECX is exactly 20, so it's 20, and in the disassembly we have 20, so we are doing it perfectly good. So those are some kind of bytes that will be generated, I suppose. Okay, so what is the next instruction? So the next is EF. Okay, so it's EF. So okay, the next instruction is EF. Um, okay. So we press F7. It's not above, so we should be trying to figure out. So this is, by the way, I want to color this one too. I want to color it in blue. So yeah, is this blue? Yes, it's okay. This blue is great. Anyway, 7. So it's EF. Okay, so this is the EF that we are searching for. So I'm going to be coloring this one too. So okay. So we see a buffer. So it's kinda known. Okay, so the EF. Okay, so it's doing pretty much the same thing. So he's registering the same thing that the other one is going to be. It's doing pretty much the same thing as the other one. So it's registering the virtual machine, and the virtual machine instruction point to the next instruction that will be pointed to by. So we can bind a disassembler for this one too. So else if the virtual machine code is equal to EF. So what are we going to be doing? So the virtual machine instruction pointer is going to be equals to the I plus 2. Okay, so it's going to be pointing to the I plus 2. What else do we have? So it's going to be doing also the same thing. So EX is going to be sub opcode, and ECX is going to be EIX ended with a 3. Okay, so and based on what the ECX is going to be having, so if it is equal to 0, then we could be doing something. Otherwise, we're going to be oh. Wait a second. It's not the same. So it started by the 2. So it's comparing what's in the CL with the 2. Okay, so if it is E0, he's going to be something. So print something else if the ECX is equal to 1 or 2, I suppose. Or let's see what is going to be happening. So it's not a 2 since we have RCX equal to 1, so there is a case of 1. Okay, there is a case of 1. So print something also just to fill it. So if the ECX is 2, I don't know. Okay, we will see if there is any case for the 2. 7. So we compare it. So there is a case of 3. There is a case of a 2. 2 is the first one. So there is a case of 2 and there is a case of 3 too. So we have 4 cases in this opcode. Else if the ECX is equal to 3, we're going to be also doing something. So we start with the case 1 that we are already executing. So if it is a 1, okay, so this is what the 1 is having. So we shift to the right the AL with the 6. So EIX equals to EIX shifted with E6. Okay. And then we move what's in the RDX plus 2 to the EDI. So this is the file descriptor and this is the buffer, and we have a right syscall. Now if you go back a little, so x64 64 syscall table, which is this one. If you go back and search for write, we see there is a lot of writes, but I want this sys write. Okay, the first one please. Yes, this one. So it's getting RDI, RSI, RDX. So the file descriptor should be with the RDI. If you go back, so this is not 64. Suppose this is yeah, so the file descriptor is in the EDI, which is the same as RSI, but in the 64, RSI, RDX, the buffer and the count. So the RDX should be, so the RDX is going to be overridden. Wait a second guys, since the EDX is going to be overridden, it's more like finding a way on how we can get back that value back, but we will see how. Anyway, for now he's going to be shifting that, so is the AL is going to be moved. So yes, it is going to be accessed somehow. Anyway, so the RDX plus 2 is going to be loaded inside of the EDI, so it's the file descriptor, and I suppose since we are doing a write, the file descriptor should be a 1 since we are trying to write to the standard output. So, and I suppose, let me check that one. So EDI, where's the EDI? So yeah, it's a 1, so it's the standard output. Moving that AL to the EIX, so we are shifting right, so it's actually E0. So we are moving that value to the EIX, and then we are accessing that buffer. So we're loading the effective address actually. So we're moving the address pointed to by RBX, which is in this case is 20. 20 plus RAX multiplied by 4. So RBX is supposed to be pointing, so this is the buffer where we will be trying to get the bytes from that we will be writing to the screen. So okay, so it doesn't matter pretty much about this buffer for now, more than just trying to mimic what this one is doing. So file descriptor is equal to 1, and since we are writing to the screen, so this is basically trying to do this thing. So he's basically trying to write those messages, I suppose, or stuff like that. I don't know, but for now he's going to be doing that. So we can just mimic that in the code. So the file descriptor is equal to 1. How much data we are going to be writing is inside of the EDX, which is 1, 2. So n equals to 1, 2. And the buffer is going to be this RBX plus RAX by 4, but we don't know the value of the value of the RBX for now. But I'm going to be just is assuming that buffer is just the. I'm going to be assuming just the buffer is the EIX for now, just with that value inside of it. Well, I'm going to just be saying that. So, and then this assembly virtual machine that I'm going to be writing, so we can get rid of that. I'm going to be writing, so basically I'm writing to the 1 or to the file descriptor, the buffer address, the n, which is already hard coded, which is always going to be 1. Anyway, so this is for the first one. So what else do we have to do? So the thing is, maybe by the way, this is going to be, so this is the buffer, but it's pointing to the RBX, which is 20. So he's actually going, if you go back to this one, so if you do CHR of 20, we see that this is a space. So basically he is writing a space to the screen, which is those spaces. Okay, this is quite interesting. But the RBX is pointing to this value. How can I map the RBX to the... Okay, I'm going to be assuming that this is going to be... Well, the thing is that it's shifted with a 6, but I cannot point that value to the registers since they are in the range of 0 to 4. I don't know, guys, if you understand the problem in here, but we need to find a way on how we can load this RBX inside of our script. Okay, I'm going to just be assuming that this is the I suppose the register should be moved since we saw those 20s in here. So since I will be seeing a 20, I will be assuming that there is a write after that. So the value that be shifted, or the value that would be used, is going to be using that one. It's just an assumption. Anyway, for now this is what will be happening, and then after the write, so I'm going to press F7 to jump on the right, so F8, I'm sorry. So we compare what the RAX with a 1. So, and suppose now if we go back to the decoder, we see there is a space, as you can see. So this is the space, so the first space. Pressing F7 again, so we jump if it is equal to 0 to this virtual machine instruction pointer. So he's moving what's in the virtual machine instruction pointer to the area, to the AIX. Okay, so I suppose, and then he's adding +2. So since he's loading the effective address, which means that RDX will be equal to RDX +2, which is already containing the virtual machine instruction pointer, which means that the RDX, which is pointing to where exactly are we executing inside of the virtual machine code, is going to be pointing to the virtual machine instruction pointer +2. So this is, we can now directly, so I equals to the virtual machine instruction pointer +2, since we already saved it in here. So yeah, so this is what is going to be happening when we press EF. Okay, so now if I want to go back a little, so this is the case of the 1. I wanted to see the case of the 3. So if it is a 3, if it is a 3, then we need to be loading some bytes of data from the memory to the EDI, and it's actually a byte. So okay, so file descriptor is exactly the virtual machine code of the I+3, and the n is equal to 1 since we saw it in here, and then we are calling a write to the buffer. So if you go back a little, so the buffer should be, what is the buffer is having exactly? Suppose if you go back a little, yeah, the buffer is in the RSI, and it's actually the RDX +2. Okay. Okay, the RDX +2. So okay, disassembly dot virtual machine dot write. I'm going to be writing exactly a file descriptor, a buffer, and well, the buffer is exactly the RDX plus 2, which is exactly pointed to by the virtual machine instruction pointer. Well, I'm going to be assuming that this is the virtual machine code at the I plus 2. And I'm going to be writing that in hex. And we shouldn't forget to add, go back to the line. Okay. That should be okay. After that, what are we going to be doing? So we're going to be now adding plus 3 instead. So the I equals to the virtual machine instruction pointer plus 3. So this is the case of the 3. Now we go back a little. So if it is a 2, which is in this case, so if it's a 2, then we're shifting the IX with how much? With a 4. And then we are moving for, well, it is an n. This is the n equals to 1. So this is the n. The x is now ended with the 3. So I suppose now we are fetching something from the register, since we are trying to access them using the index pointed to by that one. So this this time the file descriptor is going to be loaded from the register itself. Okay, so file descriptor is register pointed to by EIX. The buffer is going to be the same one, I suppose. In this case, it's going to be virtual machine code of the I plus 2, and then disassembly dot virtual machine dot write. So I'm going to be writing the same write. So file descriptor hex of the buffer and n, and we go back to the line. So this is the third case, I suppose, the second case. Okay, so if everything is working fine, we add now I plus 1, so the I should be equals to the virtual machine instruction pointer that was saved plus 1. Now if we now just go back a little, there is only one case that we didn't see, which is the case of the 0. So if it's not a 0, it's not a 3. Now if it's not a 1, then it is a 0. So if it is a 0, then we go back a little. We move into the EDX, so EDX equals to EIX. We shift right the EIX with 4, so EIX equals to EIX shifted to the right with 4. I suppose there should be an AND, which is in here, so we already did it. So EDX is also shifted to the right by 6. What else? Is the EDX ended? Nope, it's not ended. So we moved that value, and then we moved, so the file descriptor this time is going to be pointed to by AIX, so register AIX in this case. The buffer now this time is going to be accessed using the RDX, which is kinda interesting. Okay, so since it is pointed, so I'm going to be just doing buffer equals to the hex of the EDX, since I don't know exactly what the RBX is going, but I don't care pretty much about the address more than the content. So yes, so and the n is equal to 1, and disassembly virtual machine dot write. I'm going to be writing this time the file descriptor and the buffer and the um n. Yes, I think that's okay. Anyway, so yeah, after doing that, what is going to be the value? So yeah, so the I is going to be the same as the virtual machine. Yes. So otherwise, so if that none of that is working, then I is should be just I plus one, and we continue. What do you think? So I suppose we have fully reversed now the right process. Now if you go back a little, so yeah, so this is the next instruction. So if you go back, 7, 7, 7. So what is the next instruction? So it's F6. So we are going back to the F6 again, which we already reverse engineered back. Anyway, so if we try now to just get rid of that, try to run the disassembler again. So we're getting F6. So we don't care pretty much about the what's happening inside of the write because I don't have the content of the address exactly, but we have 20. So all what we have to do is check what is going to be passed before the write exactly. So we have 20. So we can just do just write a quick just to get them. So we have 0xt 2e. So we have 20, 20, and we have 2e. We have 2d. We have 2D, we have there is a lot of garbage, by the way, a lot of garbage in this virtual machine. We have also another 20. We have now some meaningful. We have 65. We have 76. We can check those values. So, for example, 65 and 76 and stuff like that. So, 0x65, for example. What is this pointing to? So it's a U. Well, it's 66 nodes actually, so it's a V. So is there any kind of V inside of this binary? So yes, there is a V. Okay. Is there what is 60? 56. So I suppose it's an A. 65 is an A. Was well, it's an E actually, not an A. So it's this E. What is, for example, let me try to check the hex of the the ord of the T to just try to figure out if it resides there or not, which is this one. See if there is the T in here or not. Well, the T is not. Something is maybe we didn't try it out. So 60, 60 though. Wait, there is the L. Okay, makes sense. The L is in there. So this is the L. This is the E. Okay, we did find something. We did find some meaningful. We have 20, which is a lot of spaces. Aside from the 20, there is also another value that have been passed a lot. So 2D. What is 2D is exactly? 2D is that one. Okay, so it's this one. It's this one. Okay, and so on. Well, that is not going to be pretty much what is the main goal for now, but we have disassembled some of them, at least. At least we have disassembled some of them. Okay, now I think it is time to go now and check the other opcodes that we should be trying to see. I know it's a time consuming process, but we need to finish all of that together. So now the next instruction I'm going to be skipping, so I'm going to skip the F6 since I know what it's going to be doing. Until I find some new opcode, I'm going to be jumping into the flow of that opcode. So I'm pressing F9. We see now that we are doing 4A, which is a new opcode. So we're going to be jumping to see what this opcode is doing. So we press F7 to just try to get exactly into it. So F7. Okay, for A we're still not there, so we are in there. Okay, we can just make this colored for A and 7, and we are there. Okay, so it's time to create a new opcode. So else if the virtual machine code of the I is equals to 0x for A. It's doing pretty much the same thing. So instruction pointer is equal to the I plus 2. If you jump back to this one, we see that he is doing the same thing, pretty much the same thing. So this time he's using the ECI, but it is the same thing. So sub opcode and ECI this time is used to do EIX and 3. Okay, so this is interesting. So if the ECI is what? So if the ECI is equal to 0, you're going to be doing something. Else if the ECI is equal to what? So it's not, he's going to be checking. So SIL is the lower part of the ECI, so if it is a 2. Okay, so if it is a 2, you're going to be doing something. So this is actually going to be doing that. So otherwise, he's going to be to the stack canary, which is the exit. So we only have 2 cases for this opcode, which is the 4A, and he's going to be shifting the EIX with 4 to the right. Is there any access to the resistor? Yes, so I'm going to be assuming that he need to end that with the 3 to get in the range of the resistors. And then ECX is loading, he's loading what's in the ECX. So ECX is going to be int from bytes BM code I plus how much? I plus 4 or I plus 2. Oh, we did that. Let's go back a little. Well, it's I plus 2, I plus 6. I plus 6. Yeah, so, and the order for sure is going to be white order it's going to be little, yeah. Okay, so we have ECX. ECX is going to be that one, so RDX is going to be 7. He's going to be adding what's in the RDX. So the instruction is 7 bytes long, and then he's moving that, or he's adding actually. Okay, he's adding. So virtual machine dot, well, this is simply, well, before adding, wait a second. So register pointed to by EIX is going to be having inside what's the value loaded by the ECX. Okay, so now if we disassemble that one, virtual machine, that's right. So he's adding what's in the register EIX. He's adding the value that is pointed to by ECX, which is this value in here, and we then add one. So this is what this virtual this is what the flow is doing exactly. Okay, just wait a second. I want to go back and check the other case too. If we go and check the other case, we see that he's going to be doing a lot of things. So EDX, well, before EDX, well, EDX is going to be having EIX. What else do we be? So EIX is going to be equal to what? EIX and shifted to the right with 6. And ended with a 3 for sure. Same for EDX. So EDX equals to EDX shifted with a 6 and ended with E3. And then he's going to be adding now what's in the EIX. So EIX is equal to register pointed to by EIX, and he's going to be adding to the register pointed to by EDX equals to the register pointed by EDX plus the value that is in the EIX. And then yes, he's completely finishing that up. So disassembly virtual machine. That's right. He's going to be adding what's in the register EDX, the value pointed to by hex of the EX. Yeah, go. Yes. And then we move what's in the RCX to the RGX again. Um, Now RCX is containing what? RCX is containing what? This is the question. Go back a little. What the RCX is having? Yeah, RCX is having the virtual instruction pointer, so the I is supposed to be equal to the virtual instruction pointer. Yeah. What else? Yes, that's it for this opcode. So I'm going to be just making sure that the I is incremented, and we continue whenever we have that virtual machine code in front of us. Yes, so if I try now to run the disassembly, I should be having now some add. Yes, add now is added, and the yes, so we're now having some more disassembly to be saying. Okay. I'm going to be pressing F9 to check the next opcode that will be executed, which is now EF. We saw what the EF is doing. F6, we saw it. 8B, that's a new one. Okay, we go inside of it. 8B. Okay. So this is the 8B. So, okay. So we press F7 and we are inside of it. So we go back. So else. Now, what does the 8B is doing? So else. If the virtual machine code of the I is equal to the 0x8b, then you're going to be doing something else, something completely not the same. Okay, what is the 8b is doing? Pretty much the same pattern always. Virtual machine is I plus 2. And then you load it, the x equals to sub opcode. The ECX is going to be equal to the EIX ended with a 3, which is pretty much the same thing, guys. Yeah, so if the EIX is equal to 3, equals to 0, I mean, which is in this case this one, so we will see what's going to be happening. So it's not a 0, so there is a 2. So print something else if the if the ECX, not the EX. So if the ECX. It's getting pretty painful now. I'm getting a lot of values. I don't know how much time you are spending trying to dissect this one, but I've already told you guys that it's going to be taking some time to do that. But let's do it together at the end, which is going to be beneficial for you and for me. Okay, so if the ECX is equal to 2, then he's going to be doing something else. So print 0, print, so if it is a 2 now we see, so print by pressing F7. Okay, so we are getting what the EIX is going to be shifted to the right with 4. We see this pattern a lot, so by trying to access the registers is always getting the index from the sub opcode, then shifting it to the right with 4 and then ending it with a 3 to get the right index that he wants to be accessing. And then he's adding to the RDX 6, which means I equals to I plus 6, which means that the instruction size is 6, if I'm not wrong. Yes, it is 6. Register now, he's accessing the register at the RAX, he's moving that to the ECX, so ECX equals to the register pointed to by EIX, and then he's doing some XOR. So okay. So this opcode is going to do XOR. So we saw the add, we saw the write, we saw the sub. Now we're showing some XORing happening. Okay, so he's XORing that value with the RDX minus 4. Since he's doing RDX minus 4, so wait a second, so ECX equals to ECX XORed with int from bytes virtual machine code. How did we do the minus? So we do the same thing that we did with the other one, but this time it's having RDX minus 4, which we already saw how to do with the minus 6. Yeah, so we do I minus 4 to how much I do we need to the I. So by doing that we are just getting exactly what we want to. So I minus 4 gives us exactly 4 bytes of data. Anyway, so this is how we do it. So and then the byte order should be little Indian, I suppose. And then we're moving the result to the register pointed to by AIX. Yeah. Is there anything that we should do? Nope, there's nothing that we should be doing. So ECX. So anyway, so the disassembly dot the virtual machine dot write. So I'm going to be writing that we did an XOR for the register pointed to by the EIX. So we XORed it with the value pointed to by the hex of the ECX, I suppose. Yeah. So that should be okay. So if we want to know now exactly now what we did, so we XORed the value that is in the register pointed to by EIX, or the value that was pointed in the register by the EIX with that value, I suppose, in the ECX. Oh, well, it's not that value, I'm sorry, it's this one. It's this one, exactly this one, yeah. Yeah. And are we making hex values there? Did we do the hex? Yes, it's hexed. Okay. Now everything should be okay for this instruction. So what is exactly now the thing that we should be knowing? Well, so for the case of the do, so this is the thing that we should be knowing. So yes, so that's it. So else I equals to I plus 1 as always, and we continue. Yes, but we have the case of the 0 to be filled. We need to go back a little. So if it's not a 2, so this is, I suppose, okay, this is the exit. And if it is a 2, then, so if it is a 0, yes. So if it is 0, ECX equals to EIX, and EIX is shifted with 6, and ECX is shifted with 4, and we are adding 3. So EIX is shifted with 6. So this is a shift with 6. And ECX is shifted with 4 and ended with a 3. EIX and ECX. And what else do we have? I equals I plus 3. What else? So the EIX is loaded, so EIX is loading the register pointed to by EIX, and then we are XORing the value in the RCX, so register pointed to by ECX equals to register pointed to by ECX XORed with what's in the EIX, and then we disassemble virtual machine. That's right, exactly this one. So XOR what's in the register pointed to by ECX with the value pointed to by hex of EIX, and then we go back to the line. Did we go back to the line in here? Yes, we did. Okay, so I suppose we have now fully reverse engineered this sub opcode too, or this opcode, I'm sorry. Do we have something to add in here? Nope, I don't think so. So I think it's time to test it. So we should be having now XOR. Okay, so we're having some different kind of values to be XORed. Okay, for now we need to finish all the program to figure out exactly each one of them. Okay, now we came to the part where um, press F9. We're good. So it's EF again. We did it. F6. AA. We did it. EF. We did it. F6. We did it. AA. EF. F6. AA. EA. F6, etc. So he's actually doing the printing job. Now, if you go back a little, so you can see he's printing something. So what am I going to be doing now is I'm going to figure out exactly where the read is and try to see where the program is going to be reading. So we need to find the read. So I remember the read is in here somehow, if I'm not wrong. Yeah, so this is the read, yeah. So this is the read syscall. Okay, so I'm going to be setting a breakpoint in the read, and I'm going to be just resetting this breakpoint from here and stopping the program and rerunning the program again. So we are in the read, but I suppose now we should be just seeing all the program printed because we have skipped that part. Now he's waiting for us to read, so I'm pressing F8, so he's waiting something, so I'm going to be giving 0, 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, E, for example. Yeah, well we have that. All around waiting because we passed the 5-second. But it does not matter too much. So yeah, for now I'm going to be getting. So I suppose now he's comparing what's in the REX with RVP, and now if we go back a little, so F7 is going back. And the thing is now, if we get back to the RBX, this is what he have read from all of that. He had read 0, 1, 2, 3. So the result of the input is in the RBX. Now here's the interesting thing. Now he's now going to be executing another instruction, which is well, the thing is, let's get back a little. So I want to check out the opcode of this one. So it's getting accessed using two opcodes. So it's this one and this one too. Do I wanted to know exactly what is the opcode for this one? But for now, anyway, so let's just try to see what this 5D is doing. So what this opcode is doing. So it's not above, it's not, okay, so this one is 5D. Okay, so it's in here, so it is doing pretty much the same thing too. But for now, we will be just assuming that the RBX is having the input or part of the input, who knows. Okay, so else if, so the virtual machine code is 5D. What is going to be happening if it is 5D? So if it is 5D, then it's going to be doing pretty much the same thing as the other ones. Always save the virtual machine instruction pointer, then EIX equal to sub opcode, ECX is equal to EIX ended with a 3, and based on the ECX we will be doing stuff. So we jump, so it's equal to 0. What is going to be happening? So if it is equal to 0, then ECX equals to EIX, and then we add to the RDX 3. We add to the RDX 3. Okay, and we are shifting right with 6 the ECX, so ECX is equal to, is shifted to the right with 6 and ended with a 3, if I'm not wrong. Yes. And then the RDX is moved to the instruction pointer again. So that means that before that the virtual machine instruction pointer is going to be modified to equal to the RDX, which is the I, which is already I plus 3, and we already also see EBP equals to what's in the register pointed to by that one. So EBP, so he's using the base pointer this time as a temporary register maybe, or something like that. So ECX, so if we now step on all of them, we see now, okay, so he's doing a read. We need the file descriptor where we are going to be writing the number of bytes and the buffer that we will be reading the bytes into. Well, we will be reading from, I'm sorry, not writing to. Okay, so he's now going to be shifting the EIX with 4, I suppose. So since he will be shifting the EIX with 4, so is he going to be using the AND this time? Yes, he's going to be ending. So he's going to be accessing another register, I suppose, pointed to by that one. Okay, so yes. So the file descriptor now. So the file descriptor is XORing EDI with the EDI and XORing it with itself gives a 0. So the file descriptor is 0. So he's reading from the standard. So he's reading from the standard input, and he is moving what's in the RBP to the RDX. What's in the RBP into the RDX, which is the number of bytes. So the number of bytes is actually inside of the EBP. Okay, cool. The buffer is going to be, I'm going to be reading inside of the RBX plus REX multiplied by 4. So that explains why he's actually pointing to the input is pointed to by RBX, because the input is going to be in there. So, and the thing is that each time he is going to be giving a 4 bytes of data. So I suppose now, since we know that there is REX by 4, so the REX is going to be changing, and since we have 4, so the read is going to be happening on 4 in 4 times. So the first time is going to be reading 4 bytes, the second time he's reading 4 bytes, the third time he's reading 4 bytes, and the fourth time he's going to be reading 4 bytes. So 4 by 4 gives you 16 bytes of data. So he's going to be having or needing 16 bytes of data to be read from the standard input. Anyway, so yes, I suppose now we should be okay with that. So we have the file descriptor. We know n equals to EBP, and we know that one, so we can just disassemble that. So virtual machine, so I'm going to also set the buffer as EIX. So disassemble virtual machine dot write. So I'm going to be writing, so we are doing a read from the file descriptor pointed to by that one from well, I don't know. Well, I'm going to be just calling it from the address pointed to by EIX to exactly the N. Well, it's not the N. It's more like finding the EBP, number of bytes which the EBP is having is register ECX. Well, it's just the same. Anyway, um, yeah. So this is what this is going to be doing, I suppose. So this is the case if it is a 0. So if the ECX now is equal to 2, which is the other case, this one is okay. So the I is going to be equal to the virtual machine instruction pointer, which is the same one. Nothing has happened. So if you go back a little, so if it is equal to, so if it's not a 3, so if it is a 2, so there is so this is an exit. So if it is a 2, okay, so if it is a 2, EVP should be equal to I plus 2, which is actually, well, he's not I plus 2, it's actually getting what's in the RDX plus 2, which is actually the value pointed by that one. So int from bytes virtual machine code I plus 2 I plus 4. So getting 4 bytes of data. Okay, little. And then we are adding 8, so I plus 8. The EIX now is, we are moving what's in the RDX to the virtual machine instruction pointer. So virtual machine instruction pointer equals to I, and then if we jump, we see that he's now getting back to the same pattern, despite now this time that the instruction, the EBP is pointing to how much data we are going to be reading as the same one, but this time it's loaded from another place. So it's the same thing. So those three values are the same, despite that the instruction that the end this time is loaded from the EBP and it's loaded from memory inside instead of a register, I suppose. So we're going to be doing also the same instruction in here. Yeah. Yeah, what else do we have? So yeah, else, as always, I equals to I plus 1, and we continue. We can try to run that code and see what happens. So we see if there is any kind of read. So we have, so it's reading in 0 and 1, 4 bytes of data that also already pointed to by this one, and then we see some kind of registers passed down. We will see. Anyway, so we have these two writes anyway. So he's how many times he read? So we have another read, we have another read, we have another read. So there's a kind of reads that it happens. So we see multiple reads happening. Anyway, so for now we can now check the next read is happening, read is happening, read is happening. And we should now just go back and set a breakpoint in here. So let's press F9 to run the debugger again. F9, F9, F9. We need to set up a breakpoint in there too again. I should have colored the read. Should have just colored just to gain some time. I don't want to always go back a little. So yeah. Okay, so I need to get rid of that, so we hit the read. No. Okay, now I don't need this one too, so I'm pressing F8. Oh, he's waiting for an input, so I'm going to be given 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So he's done. Okay, so if I press F7, now the next instruction is going to be executed 5D, but this time the RBX, as you can see, something 0, 1, 2, 3. Okay, I'm not going to be using that one, so I am now going to be just getting rid of that breakpoint so that we can skip time on how. So if, wait a second, why is he not breaking up there? Wait a second. Okay, setting breakpoint there. Okay. Wait a second. F9, so EF, F6, EF. I suppose we should haven't already written a lot of. I was still writing. Okay, so it does not matter too much about that. I'm going to be trying to see another opcode aside from this one. I'm going to, for example, to set what other opcodes did we do. So EF we did it. What other opcodes do we still have? We still haven't, for example, 7C. We didn't see this one. Let me just set a breakpoint in here and see and see when he's going to be hitting this one. So pressing F2. Okay, so pressing F2. So I'm setting a breakpoint in there. I will just also deleting this breakpoint in here so that I can let the debugger hit the breakpoint that I want. So 7C. Is he waiting for something? Nope. He did hit the 7C without. Ah, yeah. We didn't. It's not the right breakpoint. It should be in this one when we enter inside of the FC. Of this one. Okay, so we can just run F9. So now we try to run F9 again. Okay, I suppose he's waiting. Yes, he's waiting. Okay, 0, 1, 2, 3, 4, 5, 6. Well, I don't know. I don't buy it, for example. 1, 2, 3, 4, 5, 6. Stuff like that. Okay. Did he hit a breakpoint or something? Well, we have the alarm to deal with. Okay, we hit the breakpoint, and it's now E6. Wait a second. RDX plus 1. What does the RDX is pointing to? The RDX is pointing. Okay, it's 7C. It's the opcode that we want to analyze. And the RBX is actually having the input that we are trying to deal with. This is iron bytes. As you can see. Yes, it's the input. So the input is in the RBX. Anyway, so we start now dissecting this opcode and what it's doing. So else if the virtual machine code is 0x7c, so what is going to be happening? So it's pretty much the same thing. Same pattern is repeating. So I plus 2. Yeah, x equals to the sub opcode. I know a lot of I know a lot of opcodes, guys, but it's time consuming, by the way. But the more you do this manually, the more you think of how disassembling virtual machines came to a hard way. And by the way, this virtual machine, guys, is not obfuscated, and if it was obfuscated, it will be giving me a lot of more pain than this one. So it took me 5 days. This one just took me 1 day to just finish all the opcodes of the writing and reading and XORing and subbing and adding and all of that. But the hardest part is doesn't came yet. Is not coming yet. Wait a second, because you will see that the other opcodes, there is one special opcode that is literally a nightmare. A nightmare, yeah. Anyway, so ECX equals to the EX ended with a 3, and based on the ECX we start seeing some kind of pattern. So if it is equal to something, so 7, 7 pressing F7, so it's not equal to 0, So if it is equal to a 2, so we see what the 2 is doing. So this one is supposed to be doing. So if it is a 2, well, if it is a 2, well, I need to get rid of that breakpoint was set. If it is a 2, it is a 2. Yes, it's a 2. If it's not a 2, then he exits. Okay, there are two cases in this sub opcode too. Okay, so EIX equals to EIX shifted with a 4, trying to access again another register. So, and 3 ECX, ECX equals to I plus 2. Well, it's not I plus 2, it's the byte located at the I plus 2. The virtual machine code I plus 2, I suppose. Yeah. And the RDX is added with a 7, so I equals to I plus 7. Okay, so what is next? Okay, so what is next? So I equals to I plus 7. And then it's shift left. Okay, so we're shifting left the registers. So this subcode is shifting the registers. Okay, so the register that will be shifted is register pointed to by EIX, so equals to register of the EIX shifted to the left by how much? By what's in the ECX, by the value that is pointed to by ECX, I suppose. Yes. So disassembly dot virtual machine dot write dot, so it's doing e shift left for the register pointed to by EIX with the value pointed to by ECX, and then you go back to the line. If you go, and then it's supposed to be getting back to the handler. So okay, so if it is a 2, so I want to check the other case. So the other case is going to be having ECI equals to EIX, as we can see, and it's shifting the EIX with 6, and then ending it with a 3, I suppose. And then the RDX is added E for I equals to I plus 4, and then ECI equals to, so he's shifting the lower part with 4, so ECI shifted with a 4 and ended with a 3. Always shift right, okay. And then he's accessing now. ECX is equal to the register pointed to by EIX, and then register pointed to by ECI, I suppose is supposed to be shifted. Register pointed to by ECI is supposed to be shifted. Using shifted to the left using the value inside of the ECX. Yeah. Okay, so yeah, so if you go disassemble that one, so the right one, so it's actually shifting left the register in the ECI with the value that is pointed to by ECI. Yeah, so this is basically what is going to be happening. What else do we need to know? I think this is it. So yeah, so if we now go else, I equals to I plus 1, what else do we need to have? I think now we should be just continuing. Now if we try to run the disassembler again, we should be having some shift left and shift right. Well, we only have shift left for now. We see, for example, now if we try the F7, 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 we just finished that one. But let's just do B1. Do we see this B1? Did we try it? We have 0x B1. So 7C, we have it. We don't have the opcode B1, so this is a new opcode. Else if virtual machine code of I is equal to 0x B1, then we start now dissecting. So we get me to the B1, please. We did the D5. Did we did it? Nope, we didn't do it. B1. So this is what the B1 is doing. So we color it. So B1. Okay, so this is what the B1 is going to be doing. It's doing the same always thing. So I plus 2, AIX equals to sub opcode, ECX equals to EIX and 3, and if the ECX is equal to 0, then there is a pattern that is going to be happening. Else, if the ECX is 2, then another pattern is going to be happening, I suppose. So if you go there and check that, so we have two cases. So if it is 0, it's not equal to 0, and we have this one and we have the exit. So yes, we have two cases. So we start to getting this one, the case of the 2. So EIX is shifted as always with a 4. So this the guy who programmed this virtual machine is pretty interested in always shifting to the right with a 4 and ending with a 3. I've been doing that for 2 hours now. Okay, so ECX is equal to the byte that is in the virtual machine code. It's pretty much the same as the other one. It looks like it's the same one as this, the shift left, since we are seeing shift right. But I think it is just doing some shift right. So let me just guess that one. So it's doing shift right. So, and the I is +6 instead of 7. But the same thing is happening. So I +2 and EIX, register EIX equals to register EIX shifted to the right with 4 with ECX. So it's pretty much the same. I think the same thing is going to be happening in here too for the other case. Let's see if it is going. So this one is for the shift left, and this is for the shift. Okay. We need to still check the other one to see the instruction length and that stuff. We go to GZ. What do we have? So it's using EDX. No, it's not the same one. So it's using EDX. So EDX equals to EIX shifted left with a 6. AL shifted 6 to the right with 6, and then the DL is shifted to the right with 4. So EDX equals to EDX, and how much the RDX is going to be? Well, there is no I in this one. Okay. And the ECX is going to be what's having in the register of the EIX. I suppose that's shift right. So it's shifting right what's in the register of RDX. Well, EDX in here. EDX in here. This is EDX. This is EDX. And I suppose this is ECX, since we are shifting that with the, so we are getting the value that is inside of the resistor pointed to by EIX, and then we are shifting right the resistor pointed to by EDX, which is this one, I suppose, as you can see with CL. Okay, and then the I should be equal now to the virtual machine instruction pointer, since we saw that the RSI is loading that value. Now if you go RSI, well, yes, that should be the value, because the next one is the handler. So the RDX is getting back the virtual machine instruction pointer. Yes, that's correct. Um, anyway, so those are the two instructions that were in there. So I equals to I plus 1. Yeah, I equals to I plus 1, and we continue, I suppose. What else do we have? For now, I think we are doing a pretty good job there. So, what is the next one? So it's for A, we know it. So I'm going to be setting a breakpoint in here, so we know it. We know the 4A, we know the 8B, we know the no, D5 is the new. Okay, D5 is the new. Okay, D5. So what does D5 do? Okay, this is the D5. So this is the complex opcode that I have talked about. So this is the one that will be actually the core of the virtual machine. So this is the code of the virtual machine, yeah. Okay, so this D5 is going to be taking us some time, so we need to figure out exactly what it does. And what it doesn't, maybe. What it does, what it doesn't. Well, we need to figure out exactly what it do. Else, if the virtual machine code is D5, yes. Okay, D5, okay, so that's going to be virtual machine instruction pointer is equal to I plus 2. Um, okay, the same pattern, so EIX equals to sub opcode and ECX equals to EIX ended with a 3. So if the ECX is equal to 0, um, then so it's a 0, we have a 2, and we have a lot of cases, I suppose, in this one, since we have CL with a 2, and if it's not a 2, it should be a 3. So well, I only want to let's correct the layout graph. Yeah, so we have a lot of cases in this one, so I'm going to be setting all of them. So else if the ECX is 1, and else if the ECX is 2, and else if the ECX is 3. So we have 4 cases to be checking. And each one is going to be doing something, I suppose. Okay, so for the first one, so let's suppose, so the RCX is equal to 3, so for the case of the 3, it is going to be doing RAD is going to be okay, I'm going to be setting a breakpoint in here, but I'm going to be coloring this one in a better way. Okay, so I'm going to be coloring this one. Okay, so RAD is going to be having RDX plus 2. Okay, so it's actually getting the 4 bytes. Okay, so the case of 3, so I'm going to be printing something and printing something and printing something. Okay. So R8D should be equal to what? So it should be equal to int from bytes of the virtual machine code pointed to by I plus 2 to the I plus 4. And we have the byte order should be equal to the little Indian. Okay, so EIX equals to R8D, as we can see, and then EIX is equal to the knot of the EIX, which is like that. So this is knot, and then it's ended with a 7. So we end it with a 7, and then we shift it to the left with a 2. So I'm going to be just adding +1. Okay, now since we do that, so now the disassembly now should be now trying to make that work. So he's loading now the effective address of the REX plus the RBX. Now pointing to the RBX, that is actually the input, so he's actually getting part of the input. So since the REX is equal to so he's loading actually the RBX plus 1, which means the beginning of the input inside of the RSI. So means that the RSI is now also pointing to the input, as you can see, and now he's comparing them both together, and now he's going to be doing a lot of things. Now he's getting now into inside of that one. He's going to be using now to the register 2, and by the way, register 2 is also, guys, the same as register um, the same as register 1. So it's basically having also 4 bytes of data, which means that register 1 and register 2 are both 128 bits. So also that means, so that also explains, by the way, guys, so that also explains these two instructions that we have seen at the beginning, which means that how can you even move a 128 bits register inside of a register inside of the register 1. So that means that register 1 has to be 128 bits of size. Well, anyway, so for now we're going to be getting to this one. So he's actually ending the value with an 8, and now a lot of things happening, and as you can see, a lot of stuff happening. I'm not going to be stepping inside one of them, but one thing that is really interesting is this loop. Well, this loop I've been trying to debug manually, so I have set a breakpoint into this instruction. I'm now going to be trying to gain some time because the video is taking a lot of time. I'm not going to be taking 5 hours to reverse fully the virtual machine. I think now you have an idea on how to deal with it, that's for sure, but what's really interesting now, if you check that those RDI and those REX, those two values together, you see that the RDI is going, as you can see, to having byte, which is from the iron byte, which is, as you can see, byte, and the RDI is going to be having also part of what I have just written with some random values. Now the thing is that this is actually going to be looping, so it's looping and actually um, swapping a little or shuffling a little my input. So after some shuffling, it's going to be doing also some shuffling to the registers itself. Now here's the interesting point. So he's going to be moving what's in the register 1, which is iron. He's going to be putting it inside of the XMM0, and then he's going to be applying this interesting, let's say, instruction, which is push or packed shuffling. So this packed shuffling is basically going to be doing like this. So this is the 1B0. This is the value that will be using by the shuffler. So to fully understand this, so it is going to be shuffling what's in the register 2 and then putting the result inside of XMM1. But here's the thing, here's how the shuffling works, so that you can fully understand what I'm talking about. So this instruction is working that way. So it's going to be taking what's in the register 2, which are those values, as you can see, that completely kind of random because he's using them as a way to shuffle. So he's going to be so taking the first thing, which is 0x1b. So 1b is actually, so b is 11. So 11, which is 8 plus 3, which is 1, 1, and 0. So this is a b. And the 1 is actually 1, 0, 0, 0. So those are 8 bits, as you can see. So he's going to group them into 2 bits per each row. Yes, per each row. He's going to be um, pushing them together into 2, 2, 2, 2, 2, and etc. So he's going to be doing 0, 0, 0, 1, and 1, 0, and 1, 1. And like that, we have um, four groups of bits. So what he's going to be doing, so he's actually going to be shuffling the input. So he's going to be taking the input and shuffling it into groups like that. So that means that, for example, if we take the example of this one, so it's like that. So he's going to be actually, if we take the example, so if we have the example of, for example, you have four groups, for example, 0, 0, 0, 1, 0, 2, and sorry, wait a second, wait, 1, 0, and 1, 1. What he's going to be doing is that's how actually the result should be. So 1, 1 um, is going to be actually, wait a second. Is something I'm missing about the push? What about the bucket shuffling that I forgot? Wait a second, let me just remember that. What am I missing? Okay. Anyway, I think so basically, so if we take those, so actually, so the shuffling is going to be happening like that. It's going to be happening like that. So we have 0, we have a 1, we have a 2, and we have a 3. So it's actually, since we have epact shuffling for double words, so D is for double words. Anyway, so it's going to be taking 4 bytes of data, and so the result should be like that. So 0, so the byte 0 should be pointing to the byte 3, and the byte 1 should be pointing to the byte 2, and the byte 2 should be pointing to the byte 1, and the byte 3 should be pointing to the byte 0. So it's actually reversing the order of the bytes. So for example, if I give a 1, 2, 3, it will be returning to me 3, 2, and a 1. So it's basically like pointing to this shuffling order. Anyway, so this is what shuffling is going to be. So it's basically just shuffling the order of the bytes. And we can just check that. So for example, since now we have okay, since we have register 2 equals to 0, 0, 0, and 28, CD, 39, A5, we can just grab them together, and as we can see now, we will be now seeing that in the XMM0. So for example, XMM0 is having those values now, which is 1 point something, and we have a 0, and we have a 0, and we have a 0, and we can just get them all. Send the debugger view XMM registers, get them out a little. Well, it's not like that one. I don't want to get that. Well, it's not the thing that I want to get out, but it's completely okay at the end. It's not going to be a problem. Anyway, so this is basically the XMM register that we want to have. So, and you can see this is the value of the XMM1, XMM0 after the shuffling. Done. You see, it's the reversing the order. So it's reversing the order of the register. So this is what the shuffling is doing. It's just reversing the order just with the 1PH. So it's like saying I'm going to be reversing the values of the register, but with one single instruction, which is packet shuffling for double byte. So and then it's going to be going to this one and adding to the I9. Now here's the thing. Now the thing that I just figured out after 4 days of debugging for of these four blocks. So each block is going to be doing something from each of the cases. So that this, for example, for the case of the 3, it's actually going to be doing a rotation to the right. So what I did is actually I try to give it I tried to give, for example, I tried to give wait a second, give me a new one. So I try to give 1, 2, 3, 4, 5. I give it actually 16 bytes. So it's actually dividing the input into 8 bytes of data, and for each one of them, it's going to be doing a rotation to the right, and for this case it's going to be a rotation for the right, and I remember there is a case that is going to be a rotation to the left, which is the case of the 2, yes. And for the other ones, it's just doing the same things, but it's not rotation. It's just doing some random stuff that I don't understand yet. But it does not matter because that what happens is that it's doing a rotation to the right and a rotation to the left. That's what matters. Anyway, so basically it was just doing that one because basically when I try to give her, when I try to give, for example, 1, 2, 3, 4, 4, and 5, it was actually doing some rotational stuff to this input. So it was dividing it, getting some part, shuffling it, and then getting the other parts of the input and shuffling it. So it was basically some genius idea on how you can do a rotation to the right or a rotation to the left using that shuffling. And to be honest, this is the first time I see something like that, and it kind of gave me some pain just to understand what it does. So that's why it gave me a hard time. Anyway, so but the thing is that the value that was shifted with, which is the interesting part, is actually loaded inside of the EAX from the beginning. So for example, the value that will be pointed in this place is going to be actually is going to be actually, yes, uh, rotated with, yeah. So for this one, so it's going to be a rotation to the right, if I'm not wrong, of the hex of the EAX. Yeah, so it's just doing a rotation to the right, and as we can see, it was doing I equals to I plus 9, which means that this is the instruction size. Okay, now if you go back a little, so I want to go back a little. I want to go back a little. So it's doing a lot of things. Yeah, so I want to go here. So okay. So basically this is the D5 if I'm not wrong. So it's jumping in here. So okay. So for the case of the 3 we saw. So for the case of the 2, which is in this case this one. So it was doing pretty much the same thing, but as you can see it's pretty much the same thing. So the value is loaded from this one. Just using the same way, which is I'm going to be taking as the same one, which is this one in here. Okay, so this is the byte order and all of that, and this time it's rotation to the left obviously, but the thing is that it's not going to be using the same methodology as the other one, because now we are going to be adding 5 instead of 9. And the interesting other point is I need also to check the other cases because we need them. Okay, so if it's not a 3, then we have two cases, which is 1, which is the case of the 1, and the case of, so if it is a 1, what's going to be happening? Going to just try to, okay, so we have this one, which is a 3, but it's doing the same thing again. Okay, so if it is a 1, then I equals to I plus 3. But the thing is that it's not doing this time in either a rotation to the left or to the right. It was doing some random stuff that I didn't make any sense of, to be honest. But what matters is that the program keeps on executing, so that's why I'm trying to get what the counter is doing. So if it's not E1, then it's a 0. So this is the case, I suppose. Okay, now it is going to be, if it is a 0, then it should be a 4. Okay, I equals to I plus 4. Like that, we have finished this one too. Well, they actually gave me a hard time, to be honest, getting just to understand those 4 blocks. They are just giving a lot of pain. He was just using shuffling to implement rotation. rotation operation, which is kind of interesting to be honest. But okay, that was a good point. Guys, by the way, if you had time, you should be trying to just make such. Just set a breakpoint at the beginning of the block and at the ending of the block, and you can see the input that was shuffled in stand the same as it's the same operation as doing a rotation, which is a pretty interesting thing to be honest. Anyway, so yes, so let me just go back a little. So what are the different outcomes that we didn't see yet? So we have this C3. Okay, we didn't see. We can just take set a breakpoint in here. So I'm going to be just doing this one. Oh, it's not the one. Okay, this one. I'm going to be setting a breakpoint in here. So I'm not going to be setting a breakpoint. Well, we can maybe dissect that using system static analysis. So um, else if um, VM code of I is equal to C3 maybe. C3, right? Yes, it's C3. 0x C3. So it's doing the same thing, I think. Virtual machine IP equal to loading the effective address. So I plus 2 EX equal to sub opcode. ECX is going to be EIX ended with a 3, and if the ECX is equal to 0, then it's going to be doing something else. Else if ECX is going to be equal to what? So if it is equal to 0, yes, so there we have only two cases, 0 and 2. So we start with the first one. For example, if it is a 0, then ECX equals to the EIX. ECX equals to the EIX, and doing pretty much the same thing that we already been doing. And ECX is equals to ECX shifted to the right and ended with a 3, and then EIX equals to register pointed to by what? By EIX, and then he's going to be doing eCompare this time, and then setting the R12D. Okay, so by the way, this R12D is actually containing the result. So I suppose this opcode is used for checking a result of something. So after doing some kind of operations, he's going to be checking if the result is equal to some kind of bytes inside of the memory. So which is pointed to, I suppose, by this value inside of the RCX. So the thing is that we need to um, so he's going to be disassembly virtual machine dot write. So he's going to be doing a compare from what? He's going to be comparing what's in the EIX to the ECX. So the ECX is supposed to be having some kind of, well, register EIX register ECX, I suppose, something like that. Wait a second. So it's register pointed to by ECX, yeah. With register, with what value exactly? Okay, what value? The value is going to be hex of the EIX, I suppose. And the I should be added, I think. So he is adding 4. So I equals to I plus 4. So this is the value that he will be comparing to. So we need it. Yeah. What else do we have? We don't have anything else, I suppose. Yes, now we can just go and check the other case. So if it is equal, we did it. So if it's not equal, which is this case. Okay, so if it is this case, so we have EIX equals to EX shifted by 4. I suppose we should be ending it with a 3. And we are fetching some kind of value. Okay, so we are moving some kind of value inside of it. So EDI, so EIX, so EDI equal to int from bytes virtual machine code I plus 2, I plus 4, and the byte order is going to be little Indian. Okay, so this is what the EDI is going to be having. He's going to be comparing what's in the register pointed to by ArrayX. So this is assembler.vm.write. By the way, am I typing the going back to the line? Yes, I'm going back to the line. This one is not one. Rotational left, rotational right. Okay, so I need to go back to the line to this one. So okay, so I'm comparing register pointed to by EIX with the value pointed to by the hex of the EDI, and then getting back to the line. I suppose that's right. Now I want to, so we're adding I equals to I plus 7 this time. And yes, so we have just sected that one too. I equals to I plus 1. And we continue. Do we have still other some opcodes we didn't see? We should be checking that too. I think we still have, yeah. What else do we still have? Should be just tracking them down. Yeah. Okay. Okay, so we have this instruction we didn't see yet. This one is going to be okay, so if it's not equal then you go in here, so if it's equal. Okay, so okay. So this one is going to be this one is so else if virtual machine code 0x 1e. Okay, it's 1e. If it's 1e, then what is going to be happening, as you can see, so it's loading the register 1 to XMM0 and register 2 into XMM6. Then loading the effective address of the RDX plus 2 inside of the REX, saving that inside of the virtual machine instruction pointer, and then as you can see he is just swapping the values of the register, then calling that one. So this one is going to be, so the virtual machine instruction pointer is I plus 2, this one. EIX is equal to the sub opcode, ECX is equal to EIX and 3 is the same one as the other one, and what's it's actually doing is it's swapping swap register 1 register and register 1. That's the interesting thing that is happening. Register 1 and register 2, I suppose. What else? So based on the value that is loaded in there, it is going to be doing something. So what it is going to be doing, so it's ending the EIX with itself. So there's no ECX, but this time it's just using directly the EX, but I'm going to be using the ECX. Okay, so or can we use the EX? What do you think? Well, let's mimic what the code is doing exactly. So it's ending it directly with a 3. So if the EIX equal to 0, since we see this pattern in here, which is this one, so since he's comparing with a 2, if it's not a 2, is a 3. So if there is 2 and 3, that means that is 0, and there is all the other cases. So if EIX equal to 1, else if the EIX equals to 2, as if the EIX equals to 3, so 0, 1, 2, 3. So if it is E2, so let's say it is if it is E0, for example, so it's not a 0. Okay, let's suppose it's a 2. If it's equal to 2, then we should be adding 9. Okay. So if it's a 2, I equals to I plus 9. Let's suppose it's equal to 3. So if it's a 3, we add 10. Okay. I equals to I plus 10, which is the A. So we have 2, we have 3, so if it's not a 3, so he's comparing it with AA. What about the case of the 1? So this is the case of the 2. So case of the 2, case of the 3. Okay. So if he's now comparing it with AL. So okay, so he's loading the RDX plus 3, which is I plus 3. If it is not a 1. Compare the AL with the 3. Anyway. Okay, so I don't know if this case is actually for the 1 or the 2 yet. I need to figure out that. Okay. Okay, just a second. Let me just figure this out. So this is E2. So if it's not a 2, so if it's a 2, he's going to be in here. So if it's not a 2, it's a 3. So if it's a 3, he's going to be executing this one. So if it's not a 3, he is going to be loading the effective address. Okay, I'm going to be just assuming that this is for the 0, for example. So RCX is equals to I plus 3, which is the same. I'm going to be just using always 32-bit value. So ECX equals to I plus 3. We add 8, so I equals to I plus 8. So if we compare the AL with 1, the RCX should be equal. So it's conditional move if it's not equal to 0. So conditional move if it's not equal to 0. So if it is equal to 0, then he's adding 8. Okay, so this is the case. Okay, so it's embedded inside of, both of them are embedded inside of the same block. So if it is equal to EX equals to 1, then I equal to I plus 8, yeah. So otherwise it's going to be I equals to I plus 3. He's not going to be overriding that value. Yes, so that's another interesting way of embedding two conditions inside of the same block. Okay, so I suppose now this is going to be just comparing it with the AL. So if it's not equal to 0, he's going to be just getting back to execute. So he's saving the virtual instruction pointer, and then he is going to be executing some kind of flow based on that one. Okay, so should be getting back. Yeah. So this is going to be just executing again what the 0xAA is going to be doing. So it does not matter. So for now, so this is what we need to be knowing. So yeah. So else I equals to I plus 1, and we continue. Okay, I suppose we have fully just now. What is the problem? Wait a second, is there any kind of problem? Okay, so we have a problem in here. So we have a kind of problem. Okay, now so if you try to run the disassembler, so okay, so just mark that. So what do we have? Okay, so if you try to search for the compare, okay, so we search for read. Okay, so at this point we have fully disassembled what the virtual machine is doing. Okay, now what matters now is since we have that. Okay, so yes, so at this point we have that one. Okay, so we have the read now. So the read, since the first reads we saw, so is actually reading 4 bytes of data. So as I have explained, so it's actually going to be reading 16 bytes of data. He's going to be taking each 4 bytes into the shuffling process by rotating them left and right. So as we can see, rotate left and right. So it's already there. Now here's the thing: after just disassembling what the virtual machine is doing, I came to a huge problem, which is trying to make sense of the code that is in there. So at this point, I tried to use ChatGPT to just figure out what the algorithm was doing, and ChatGPT actually did a good job trying to figure out what the patterning was doing. And he gave me actually potential three potential targets for algorithms. He gave me IES and he gave me tiny encryption algorithm, which is the case in this place, which is actually the algorithm that was executed there was the tiny encryption algorithm. So I don't know if you know it or not, but it was actually the one that was executed right there. So this is the algorithm so that was executed. So we needed to figure out exactly what this one is doing. So I actually take the encryption and the decryption. So what was doing was he was encrypting the data. So what was the data that was encrypted? So this is the interesting part. So if you take a look at the fread, so the read, I'm sorry. So the read is actually having some values. And I tried to use also prompt ChatGPT to give me, for example, the key and the block that was encrypted. So just for the people who don't know what the tiny encryption is doing, so it's basically taking a key size of 128 bits, which is equal to 16 bytes of data, and taking also a block size of 64 bits, which is 8 bytes of data. So it's actually going to be taking the input, which is equal to 16 bytes of data, and dividing it into two blocks of data, which is 8 bytes and 8 bytes, and he's going to be encrypting each 8 bytes of data inside of the algorithm using the tiny encryption algorithm. Then he's going to be comparing them to these two values. For example, for the first block, he's going to be Comparing it with this one, with these 4 bytes, this and this 4 bytes is equal to 8 bytes. And for this second one, so this one is useless, so this value is useless. And for the latest 8 bytes, he's going to be um, decrypting using that one. But here's the things now. If we try to get, for example, the decryption, what we need to give is to give the encrypted data and the key. So the key seems out to be this one. So this is the key. So those 4 bytes and those 4 bytes. And also, I suppose if I'm not wrong, this value is also included. So I try to actually play around a lot of around those garbage values, and we also have this one. So I tried to do pretty much a lot of trial and error while trying to figure out exactly what the algorithm was doing. And I also needed to figure out exactly what is the delta in this case. And the delta in this case seems to be E0 FF, since it was repeated a lot. So yeah. So at this point we can now, for example, write a solver for this one. So I'm going to be calling this one solver.cpp, for example. I'm going to be writing that in CPP. Yeah, so this is solver.cpp, I suppose. Yeah, so I'm going to be including um, bits slash standard C++ dot h. So int main, so we return 0. We get this decryption algorithm as it was. So I'm going to be changing what is exactly, I believe, is in this one. In this case, it is 0x. Yeah. So this is the sum, and it's actually saying that the sum should be shifted to the right with 5, which is the same as multiplying it by 32. Yeah. So this is the delta, and so yeah, so now all we have to do is create the key. So it's an unsigned 32 type, which is now the key. So the key is actually having E4, so the key is going to be, yeah, so we go back to read, we go back to this little above, yeah. So 0x80, so it was this one. 0x82 5D, and this one. And this 28. So this is the key. So for the first encrypted values, we have v of 2 is actually going to be the first compared values. So fb9 and a25. So those two values right there. What else? So yeah, so now we can run the decryption. So decrypt the v with the key. So we need to also not forget to add semicolon. Yes, so now we can, for example, try to decrypt the first one. So I'm going to be printing percentage s of the v. Okay, if we try now to decompile or compile that, so solver dash o, I'm going to be just calling it solve. So this is a warning. What is this warning is saying? Word overflow. Delta. Is solve is working? Well, as you can see, um, this is the second hardest part of the challenge, is that the decryption does not work. So that means that at this point I thought that ChatGPT was making some bullshit, just trying to mistake me into thinking that this is a tiny encryption algorithm while it's not. But it seems out to be that the disassembly of the program of the virtual machine was doing some customized stuff. So this is took me 3 days just to figure out, by the way, because I was literally debugging and redebugging the four blocks that I showed you in IDA, which are those four, just to make sure that he was doing exactly what I thought. And it comes out to be that there is some kind of, as you can see, if we just go back shift right, there is some kind of register that was having, if we go shift right 0, as you can see, shifted 0, it was shifted with a 5. If we go back to the algorithm, just a second, where is the algorithm? So it's using shift with a 4 and a shift with a 5, as you can see, shift right and shift left. So shift right with a 4 and shift right with a 5. But the thing is, for example, so yes, so it was doing that. But what about shift left? As you can see, so it's a 4, still a 4. There is a case that was a 1, pretty sure. Is there any 2? Yes, this is a 1. It was a 2, as you can see. And was shifted to the right with a 2 and a 3. So there was a case where he was shifting to the left and shifting to the right. He was shifting to the left with a 2 and shifting to the right with a 3. So that means that in this case, there was a sub case, and that case actually was, while I tried to debug that, was in the encryption the 22 operation. So in the 22 operation, instead of shifting to the right with e5 and to the left with a 4, he was doing a shift to the left with a 2 and a shift to the right with the 3. So if we want to inject that in the decryption, so since in the encryption it is the 22 operation, in the decryption it should be the reverse way, so it should be the ninth. So it should be the ninth operation. So this is what I did. So I just do, so if the I is equal to 9, then you're going to be doing some special operation. Else you are going to be doing, so else you're going to be doing this operation. Otherwise you're going to be taking this operation in here. Just wait a second and just trying to make sense of it. So it was a shift to what? Let me just go back to this assembly. So shift to the left with 2, shift to the right with 3. So this was a 2 and this was a 3. So this is the only thing that, so it was a customized tiny encryption algorithm. So if we try now to run the same program, so okay, just what is the problem now? Wait a second, did I inject the right delta? Did I inject the same delta? Oh no, it's not the same delta. Wait a second, what am I doing? My bad. And now there's no warning. Okay. Yes, and you can see this is the first part of the flag, which is this one. Now, how can we figure out the second part? So the second part, I was actually just now, we can just directly, so get this v0, so we just change the values and rerun the value again, rerun the algorithm again. So it's now we go to the compare again, so those values again, so we take them, so 0x and v1 equals to this value also. Now if we print them together, so we take that and we print, we decrypt and we print again. So if we compile, what is, oh, okay, never mind. Uh, as you can see, we see the first part, which is this one, and this is the second part, I suppose, which is this one, if I'm not wrong. So this is supposed to be the input, and we can check that. Okay, just let me go back. Invalid tryharder. I think there is part of the flag. There is not. Here we run this over again. Pretty much, we can make sense. Okay. This one. Maybe this one is part of it. I don't remember exactly, but one of them worked for me. Okay, just let me try this one. Yes, so this is the flag. Okay, anyway, I think there was pretty much a lot of things in this virtual machine. I know it's been painful. We've been trying to reverse a lot of opcodes inside of it. Guys, if you make sense of this virtual machine, then I'm pretty sure if you are a CDF player or if you are someone who wants to dig deep inside of virtual machines and who wants to, let's say, have some kind of patience to reverse engineering, then playing this virtual machine can be a good start if you try to play it on your own again after you watch the video, or after if you want to make sense of some stuff. So for example, the complex parts of this virtual machine is that I want to gain some time, because if I'm going to be digging deeper inside of each one of them as I did for the ride and as I did for the other opcodes, it's going to be taking my video hours and hours. It might be turning into a stream, maybe, by the way. I don't know. I might be streaming too in the few next weeks too. I don't know if you are aligned with the idea or not. You can just type, or just you can just write me in the comments if you think that streaming is a good idea or not. Otherwise, if you have any kind of problem, any kind of question, any kind of anything, you can just either just drop a message on Twitter or write a comment in here. And I hope this video just let you learn something new with virtual machines. Anyway, that's it. I think this is the end. Bye.